Now we'll talk about a new performance measure called steady state error. Up to now, we talked about other performance measures in previous videos, and they all had to do with the behavior of the system up to the point where it settles. So during the transient response phase, the steady state error is out here in steady state. It's meaning as time goes to infinity. The other difference is that all these other performance measures that we talked about before were in reference to a step input. When it comes to steady state error, we'll consider a couple of other input types. And here's the general method. First off, you have to define what we mean by the error. What is it you're going to want to minimize, probably? And we'll talk about that in a second. Next, you want to express that error in the Laplace domain in terms of a specific input, because there might be more than one input. When you do that, you set all other inputs to 0. So we'll end up with some, this error in the Laplace domain is some function of s, right? Then we apply the final value theorem. And I talked about that in module 2, quite a ways back. Here is the final value theorem for this E. The limit as time goes to infinity in the time domain is this limit in the Laplace domain. You take that big E, multiply it by s, and take the limit as s goes to 0. That's the general method, these 3 bullet points. And like I said, we'll now consider more than just the step. We'll now consider the ramp and the parabola. And if they're all unit stepped, etc., it's just 1 over s squared, and 1 over s cubed. Or in the Laplace domain, it's 1 over s to the k plus 1, where k is the power of t in the time domain. Typically, the errors we talk about will be the difference between input r, which can be considered your desired output, and y, the actual output. We call it the tracking error when we're actually interested in with respect to the r, the error with respect to the r. In this case, here's how you express that big E. It could be put in terms of the usual closed loop transfer function, which I'll call T, not to be confused with the disturbance input. This just means the transfer function of the whole closed loop system. So here's the expression for the big E with respect to the input R. If the error with respect to the disturbance, the time domain it's r minus y, but we set r to 0 when we're examining another input. So it's just minus y. So here's that transfer function, and let me go back to the block diagram that comes from. I'm looking at, remember the error was minus y? I'm looking at it with respect to this T sub b, this disturbance input. In that case, this process here is the forward path gain, and these two guys, the product of these two guys are the feedback path. So my overall transfer function from t to y is going to be this t over 1 plus this g times this product. And that is this. Here's the transfer function part. And y would then you'd have to multiply by the input, and you've got the minus. Just a good number of my students, the problems they had with these problems a lot of times it's just doing the block diagram correctly, getting the correct transfer function and expressing this E correctly. I'll talk a little bit more as we go on about that. Here's a useful tip, by the way. You know, you're trying to get this thing. Remember, this was that general formula where G is the forward path gain and H is the feedback path gain. Here was the formula for that whole transfer function, closed loop transfer function. Well, G and H have numerators and denominators. You can do this little bit of algebra ahead of time. You kind of have a formula for it. The denominator is just the product of the two denominators plus the product of the two numerators. Numerator is the numerator of forward path gain times the denominator of the feedback path gain. Take this as an example. Here's the G, here's the H. Well, the denominator is these two denominators combined. S times S plus 4, S plus 6, plus the product of the two numerators, just 100. And in the top, I have this 100 times that S. Write it on a formula sheet, memorize it, whatever. It'll save you some time. So here's an example. For this little system, and where this G sub P equals 1, find the unit step tracking it. That's part A. Part B, find this GP constant that'll make that unit step tracking error 0. So let's use our little trick here. Find the closed loop transfer function, this part. The denominator is going to be S times S plus 2 times S plus 1 plus 4 times S plus 2. Numerators. And in the numerator, this numerator times this denominator. See how easy that is instead of save some algebra steps. And since it's got this thing in front, that's got to be in front also. That's the total R to Y transfer. Now, we're looking for the tracking error, which means with respect to R. Error is R minus Y. Here's what it is. This T is that transfer function from the previous chart. Here is the steady state error using the final value. When R is a unit step function, it, in the Laplace domain, that's 1 over S. And final value theorem says multiply all of this by S. Well, in this case, the S's cancel. So when I evaluated at S equals 0, I just get 1 minus T evaluated at 0. T evaluated at 0 is. Here was that whole transfer function. Evaluated S equals 0, what do I get? 0.4 times 0.1, etc. Well, this whole mess here is 0 because this is that S. And so the bottom is 0.4 times 3. Do the arithmetic, and T evaluated at 0 is T sub P over 30. Error then is 1 minus that. So when BP equals 1, the error is 29 over 30. Just a little bit less than 1. If I want that steady state error to be 0, I just make G sub P equal 30. One more example. Here's the block diagram. Find the steady state error to a unit ramp in the disturbance. Let's see here. When I'm looking at the error with respect to T sub B, I set R to 0. The error is R minus Y, so it's minus Y. Keep the minus sign. What's the transfer function from T to Y? Well, this is like my T. This is like my H. I got the minus sign in there. So it is let's see, the denominators, the product of the denominators, plus the product of the numerators, 50s plus 2s plus alpha. The numerator is this guy's numerator. This guy's denominator. And to get at y, the minus y, I need to also multiply by t sub d in the Laplace. It is a unit ramp. That's 1 over s squared. Final value theorem says take all that s, multiply by s, and take the limit as s goes to 0. We've got an s here, and an s here. Those two s's cancel that 1 over s squared. And let's see. When s equals 0, this whole front part goes away, and I've got a 2 over 50 times 2 times alpha. Whole thing is 1 over minus 1 over alpha. Okay, we'll do this special case when you have unity feedback in another video.